We want to study one element in the periodic table of the elements called sodium. You can find sodium in the first group of the periodic table of the elements. Under lithium, it is in the third period. So in the first group, called 1a, in the first period you have hydrogen, in the second period you have lithium, and in the third period you have sodium, Na, which the Latin name is natrium. That's why we use the symbol Na, but in English it is called sodium. And below sodium you find K, potassium, which is in the fourth period of the periodic table of the elements. Sodium has 11 protons because the protons make the element. So that's the same as the atomic number. And it has 12 neutrons to make its nucleus stable. And we know that protons and neutrons are subatomic particles that you find in the nucleus of an atom. The next question we have to answer is, how many electrons do you need to make sodium a neutral atom? We know that a neutral atom has the same number of protons as the same number of electrons. So as sodium has 11 protons, it needs exactly 11 electrons. We want to answer the question, what is the electron configuration of Na sodium? We saw that Na, sodium, with the atomic number of 11, is in the third period, group 1a of the periodic table of the elements. What does this mean for the electron configuration of the atom of Na? The fact that Na is in period 3 means the atom of Na has 3 shells in which you can find electrons. And what does it mean that it is in group 1a? This means that there is 1 electron on the outer shell of the atom. Though this is where we will have to put the 11 electrons for the sodium atom. 1 shell, 2 shells, and an outer shell. And we know that on the outer shell there will be only 1 electron. We show now the electron configuration of sodium on Andy's electron configurator. We add the 11 electrons for sodium into the 3 shells of the sodium atom. The first shell can hold only 2 electrons. The second shell can hold a total of 8 electrons. So in shell 1 and 2 together we have 10 electrons. And therefore the 11th electron for sodium has to go into shell 3. We are now looking at the subshells of each shell. Shell 1 has 1 subshell called 1s. Shell 2 has 2 subshells called 2s and 2p, and shell 3 has 3 subshells called 3s, 3p, and 3d. Within these subshells there is space for only a limited number of electrons. So within subshell S there are 2 electrons. Within subshell P there can be up to 6 electrons, and within subshell D can be up to 10 electrons. Now let's see how this looks on Andy's electron configurator. We have here the 3 shells, 1, 2, and 3, and here we have the subshells S, SP, and for shell 3, S, P, and D. The subshell S has space for 2 electrons. The subshell P has space for 6 electrons, and the subshell D has space for 10 electrons. We place the first electron for sodium into the smallest shell number 1, in subshell S. This is shown by a red pin, and this red pin is pointing upwards. This should indicate that the first electron has a clockwise spin, like a basketball that can spin on your finger clockwise. Subshell S has space for 1 more electron, but this electron has to have a counterclockwise spin, which we indicate with a red pin that points downward. So please remember, subshell S has space for 2 electrons, one with a clockwise spin and the second one with a counterclockwise spin. For the next 2 electrons we have to add into shell 2, subshell 2s. There's nothing new. 1 electron has a clockwise spin and the second electron has a counterclockwise spin. A pair of electrons in the same subshell, one with a clockwise spin, the second with a counterclockwise spin, form an orbital. So what you see here are 2 s orbitals, one in shell 1 subshell S and the second in shell 2 subshell S. An orbital is the space around the nucleus of an atom within a subshell containing 2 electrons, one with a clockwise spin, the other with a counterclockwise. In shell 2 we have 2 subshells, 2s and 2p. The subshell P has space for 3 orbitals with 2 electrons each. And as you know, 1 electron within an orbital has a clockwise spin, and the other electron in the same orbital has a counterclockwise spin. Here you see the subshell S with its 1 orbital, 1 electron with a clockwise spin and the other electron with a counterclockwise spin. And for P, subshell P, you see the 3 orbitals pairing each one with a clockwise spin and the other with a counterclockwise spin for a total of 6 electrons. 1, 2, 3, 4, 5, 6. How are these three orbitals in subshell P filled with electrons one after another. Here's an example. We have to put 3 electrons into subshell P. So here you see the 3 orbitals, and the question is, where does the first electron go, the second, and then the third? There are 2 possibilities. A, first orbital 1 filled with 1 electron with a clockwise spin, and then with a second electron with a counterclockwise spin, and the third electron goes into the second orbital. Or all the orbitals, this is case B, are filled first with 1 electron with a clockwise spin, and then the 4th electron would go into the first orbital with a counterclockwise spin. So that are the 2 possibilities, and nature decided either A or B. Let's summarize how the electrons are filling these 3 orbitals of subshell P one after another. The first electron goes into orbital 1 with a clockwise spin that is indicated with an up arrow. The second electron goes into the second orbital with a clockwise spin. The third electron goes into the third orbital also with a clockwise spin. The 4th goes into the first orbital with a counterclockwise spin. The 5th goes into the second orbital, also with a counterclockwise spin, and the 6th electron goes into the third orbital, also with a counterclockwise spin. That electrons in the same orbital have to have a counterclockwise spin is called the Pauli exclusion principle. Pauli exclusion principle. This is how the electron configuration of sodium looks in Andy's electron configurator. In shell 1, subshell S, 2 electrons with opposite spin forming 1 orbital. In shell 2, subshell S, 2 electrons with opposite spin forming 1 orbital. In shell 2, subshell P, 6 electrons in 3 orbitals, and each orbital contains a pair of electrons with opposite spin. Finally, in shell 3, subshell S, 1 single electron with a clockwise spin. The electron configuration for 11 sodium Na is written as 1s2, 2s2, 2p6, 3s1. What does this mean? The 2 means the shell number. The P is the subshell letter, and the 6 is the number of electrons in this subshell. So this means in shell 2, subshell P are 6 electrons. You can read now for yourself what 1s2, 2s2, 2p6, 3s1 means. You can also show the electron configuration using an orbital box diagram. And this is how it looked like. And you are aware that, for instance, 2p has 6 electrons. Pairs of them are in the 3 orbitals of subshell P. Please also note in subshell 3 there are still 2 more subshells which are unoccupied. One is called P and the third one is called D. And P has of course 3 orbitals for a pair of 2 electrons each, while subshell D has 5 orbitals with 2 pairs of electrons with opposite spin each, so it has space for a total of 10 electrons.